Use. Structures are usually first classified by the use for which they were designed: residential, commercial, industrial, and rural. Each type may have subtypes. See Table 9.5. Table 9.5, examples of use subtypes. Residential includes single family, condominium, duplex, triplex, fourplex, and apartment. Industrial subtype includes warehouse, self-storage, mini-storage, light manufacturing, and heavy manufacturing. Rural subtypes include barn, grain storage, and feedlot. Commercial subtypes include retail store, convenience mart, fast food restaurant, restaurant tavern, supermarket, discount store, office building, medical office building, bank, credit union, movie theater, auto service, garage, hotel, motel, Holiday Inn, hospital, I'm sorry. I couldn't read.
What were you going to
Hotel, motel, Holiday Inn.
Oh.
But it's hospital.
Oh.
So. Sorry. Giggle break. Construction type.
Okay, hold on. I'm not sure if these are our construction types in our system. So
Buyer beware.
Buyer beware disclaimer, so go ahead.
Hashtag asterisk. I'm reading from the page.
Okay.
Construction type. Construction type refers to the structural characteristics of a building, particularly the materials used in frames and walls and the degree of fireproofing. The letters A, B, C, D, and S are frequently used to designate 5 recognized structural types. See Table 9.6.
You go ahead and read it.
Class A construction type has fireproofed steel frames that support all floors and roof loads. Walls, floors, and roofs are built of non-combustible materials. Class B construction type has fireproofed reinforced concrete frames that support all floor and roof loads. Walls, floors, and roofs are built of non-combustible materials. Class C construction types has exterior walls built of non-combustible materials, interior partitions and roof structure are built of combustible materials. Floors may be concrete or wood frame. Class D construction type has exterior walls that are wood or wood and steel frame. Walls and frame are generally built of combustible materials. Class S construction type has a metal frame without fireproofing, but of incombustible construction, has a metal skin or sandwich panels. Construction quality. Construction quality refers to the types of materials used and the quality of workmanship. Structures of better than quality cost more to build per unit of measure and command higher prices. Go outside. Go. Structures of better quality cost more to build per unit of measure and command higher prices. Construction quality, however, is the most difficult criteria to apply. Base specifications should clearly identify the characteristics that distinguish each quality class, and assessors who assign construction quality ratings should be thoroughly familiar with those characteristics. Floor area. Smaller structures usually have higher building costs per square foot than larger structures, because in larger structures fixed costs are spread over more area. Larger structures require fewer linear feet of wall surface per square foot of structure area. See Figure 9.2. Variations of building costs with size can be treated in one of 2 ways. Either cost tables can be developed for various square foot increments, or a base rate can be specified for structures of standard size and size multipliers developed. For example, if the base specification for a minimal quality one-story building is 1,000 square feet, the base rate for this construction class is $78.16, and size multipliers could be developed as shown in Table 9.7. The cost of reconstructing a 1,200 square foot building is then computed as 1,200 times $78.16 times 0.966, which would be equal to $90,600 rounded.
We'll have to see where they get that .966 from. I don't know about that number.
It probably comes from the table in 9.2 or 9.7.
Okay.
It comes from Table 9.7,
Okay.
developing size multipliers on the next page.
Okay. So that's just an example.
And Figure 9.2 looks like
You can read that. Those are good things to remember.
the Figure 9.2.
Yeah, you can explain it.
Oh, I can try.
Well, you can read the math,
Yes.
read the math out.
So Figure 9.2 is area and perimeter ratios. Building 1 is 100 feet by 100 feet.
That's what? Oh, okay. You're reading the diagram now. Okay. Okay, go ahead.
Building 2 is 200 feet by 50 feet. So building 1, the area is 100 feet by 100 feet is equal to 10,000 square feet. Perimeter is 100 foot plus 100 foot plus 100 foot plus 100 foot equals 400 linear feet. Please don't let him tear up that string. Ratio. The 10,000 square feet divided by 400 linear feet equals 25. It just says ratio, 25.
How'd they get the 400? Well,
The 400 is the linear feet, which is all four sides added up.
The walls. Okay, so it's, you divide the total square feet to get the ratio, you divide the total square feet by the perimeter amount. Okay. Yeah, okay, so repeat that when you read this next example for building 2.
What do you want me to repeat? I'm sorry.
Where did those numbers come from? The 10,000 divided by 400?
Okay. Well, I did, but okay. For building 2, the area is 50 feet times 200 feet, which is 10,000 square feet. The perimeter is 50 feet plus 200 feet plus 50 feet plus 200 feet, which is equal to 500 linear feet. So the ratio is 10,000 square feet divided by 500 linear foot, which gives you a ratio of 20.
So ratio is total square feet divided by the perimeter.
The linear foot.
The total perimeter. Total of the perimeter. Okay. It could show up on the test. I don't know.
Well, structure shape is, we're fixing to talk about that in the next section. I see some stuff coming up here that maybe it'll help.
Yeah, those are important. Those are going to come up on the test.
Okay. Well, Table 9.7 talks about developing size multipliers.
Okay.
So your floor area in square feet.
You don't have to read that one, I don't think. No,
Well,
you don't have to read it.
Well, you wondered where the 0.966 came from on the page prior.
It's from the table. Yeah. I don't think we have to read that table. Okay, go ahead. Yes. Go down to structure shape.
Okay. So structure shape. Among rectangular structures, a square structure is the most economical to construct. The greater the deviation from this shape, the higher the per square foot cost of construction. This reflects the effect of area perimeter ratios. The higher the ratio, the lower the the per square foot cost. The examples in Figure 9.2 show a square structure 100 feet by 100 feet. It has 25 square feet of area for every linear foot of wall, and that another structure 50 feet by 200 feet has 20 square feet of area for every linear foot of wall. Any structure with a lower ratio of square feet of area to linear feet of wall, in this case the non-square structure, has a higher overall cost per unit, or the smaller the ratio, the most costly per square foot the improvement is to construct. Construction costs also vary with roof shape. The least costly is a flat roof. More expensive is a steep, pitched roof with many ridges, valleys, or dormers.
Well, in reality, that's not really true. The least costly is a flat roof, only if covered with roll roofing. But if you cover it with tar and gravel, it's more expensive. So, but what they're talking about really is the pitch adds area to the roof. So the steeper it is, the more shingles you're going to use. The more covering, I guess you could say. So, okay, go ahead.
Story height. Structure costs often vary with story height. For example, a 2-story residence ordinarily costs less per square foot of living area to construct than a 1-story residence because the cost of the roof and foundation is spread over a larger living area. Classifications used in the comparative unit method should be based on some combination of the above criteria. Criteria not used in the classification scheme should be used for adjustments. For example, residential structures may be classified by design, construction or wall type, and quality class, with adjustments made for size, shape, and story height. Similarly, commercial structures may be classified by design, wall type, and story height, with adjustments made for construction, quality, size, and shape. A typical or benchmark structure should be determined for each class and described in a set of base specifications. Construction costs for the benchmark structures should be then gathered from local contractors and builders by using the unit in place or quantity survey methods and divided by square feet to arrive at base rates. Adjustment factors should be determined for size, area perimeter ratios, or any of the other classification criteria above not used in defining separate structure classes. Adjustments also must be provided for variations from base specifications. Adjustments should be derived from detailed cost estimates provided by builders and contractors. If, for example, a structure has a shake roof, although base specifications assume an asphalt shingle roof, the cost manual should specify the per unit square foot difference in construction costs. Finally, the manual should be tested on recently constructed structures of known cost and adjustments made as necessary. These structures should not be the same as those used in development of the manual. Assessors should be trained to use the manual and the accompanying property record form. The manual also should be regularly updated to reflect changing structure costs. Cost trending and indexing. Costs vary geographically over time, yet cost schedules reflect a different specific time. Costs vary geographically and over time, yet cost schedules reflect a specific time and location. Most commercial cost estimation services contain time and localization indexes. Cost indexes are also published in a number of trade magazines and government publications. To develop a cost trend factor from the cost index, divide the index for the current date of appraisal by the index for the base date, that is, the cost date of the current manual. For example, assume that the index for the assessment date is 184.3 and the index for the base date is 159.4. The cost trend factor for time is 184.3 divided by 159.4 equal 1.1562. Location trend factors are derived in the same way, although most cost estimation services report them directly. For example, one area may have a location factor of 0.956, indicating that construction costs are less than in the base area, but another may have an index of 1.042, indicating that costs are higher than in the base area. To combine a time with a location factor, simply multiply them together. For example, 1.1562 times 1.042 equals 1.205. When published, cost trend factors do not adequately reflect local conditions. The assessor can develop local trend factors. To do this, the assessor determines current construction costs for a benchmark property in each structure class. The benchmark structures usually correspond to the base specifications for the class. Cost trend factors are then calculated by dividing current construction costs by previous costs. Assume, for example, that the current cost of constructing a one-story, 1,500 square foot single-family house of average construction quality in accordance with base specifications for the class is $109,300. The cost based on the current manual is $103,850. The appropriate cost trend factor for the class is $1,009,300 divided by $103,850 equals 1.0525. This factor should be applied to costs based on the current manual or applied against base rates and other costs for the structure class. The latter is particularly effective when adjustments to base costs are maintained as percentages or multipliers. Cost trend factors may work satisfactorily for several years, but costs used in manuals must be periodically updated item by item because labor and material costs change at different rates. Manuals trended over a long time lose accuracy, consistency, and credibility. Summary. The cost approach is based on a comparison between the cost to develop a property and the value of the existing property or a similarly developed property. Because the real estate market relates value to cost, the cost approach reflects market behavior. This approach is typically most applicable in valuing new or relatively new construction when the improvements represent the highest and best use of the site. The site value is well documented and supported, and little or no functional or external economic obsolescence is present. When the cost approach to value is used, a few basic points must be considered. First, cost is not necessarily value, nor does it create value. As discussed earlier, many other factors enter into estimation of value. On the other hand, the cost approach is a comparative approach. Not only are cost data derived from newly constructed comparable properties, but, as discussed in the following chapter, market reaction to comparable properties is used as a standard form which to estimate depreciation. The process for valuing property by the cost approach include the following 6 steps. Number 1. Estimate the land site value as if vacant and available for development to its highest and best use. The second in the process for valuing property by the cost approach is to estimate the total cost new of the improvements as the appraisal date, including direct costs, indirect cost, and entrepreneurial profit from market analysis.
Here comes the UPS guy bringing presents.
Do you want to greet him at the door? He is your bestie. Oh, it's Jordan's book. Are you ready?
Yeah, I'm recording.
Oh, God. The third in the process for valuing property by the cost approach is to estimate the total amount of depreciation attributable to physical deterioration, functional obsolescence, and external economic obsolescence. I hate that word.
Obsolescence?
Yeah. The fourth in the process for valuing property by the cost approach is to subtract the total amount of depreciation from the total cost new of the primary improvements to arrive at the depreciated cost of improvements. The fifth in the process for valuing property by the cost approach are to estimate the total cost new of any accessory improvements and site improvements. Then, estimate and deduct all depreciation from the total cost new of these improvements. And the sixth in the process for valuing property by the cost approach is to add the site value of the depreciated cost of the primary improvements accessory improvements, and site improvements to arrive at a value indication by the cost approach. The assessor must conduct a thorough physical survey to obtain data on the construction, quality, condition, and adequacy of each component of the improvement. The assessor needs to make a decision on the functional utility of the improvement, its ability to satisfy market standards and demand. Costs consist of all direct and indirect expenditures necessary to complete construction, as well as entrepreneurial profit. Direct costs include materials, labor, supervision, equipment rentals, and utilities. Indirect costs include architectural and engineering fees, title and legal fees, insurance, interest and fees on construction loans, taxes incurred during construction, advertising and sales expenses, and reasonable overhead and profit. Entrepreneurial profit is the difference between the cost of development and the market value of the completed property. There are four types of cost: reproduction cost, replacement cost, historical cost, and trended historical cost, sometimes referred to as reproduction cost. Reproduction cost is the cost of producing an exact replica of the building or improvement using the same or very similar materials, design, and workmanship. Replacement cost is the cost of producing a building or improvement with the same utility but using modern materials, design, and workmanship. Historical cost is the cost at the time a property was originally constructed and placed in service. Trended historical cost is historical cost factored by reference to some current index for property components. The following are methods for estimating cost. Number 1. The quantity survey method requires a complete itemization of all construction labor and material costs by components and subcomponents and of all indirect costs. It is the most accurate and least used method of cost estimation. The second method for estimating cost is the unit in place method. It expresses all direct and some indirect costs as a unit, such as cost per square foot and cost per linear foot. Constant cost components such as water heaters are expressed as lump sums. It is the second most accurate method for cost estimation. The third method for estimating cost is the comparative unit method. It sums all direct and indirect costs and creates a unit of comparison such as cost per square foot for each quality and type of construction. I read that wrong. I'm going to repeat that. The third method for estimating costs is the comparative unit method, which sums all direct and indirect costs and creates a unit of comparison such as cost per square foot for each quality and type of construction. There, that's better. This method is the most widely used in both single property and mass appraisal by appraisers, assessors, calculating the cost approach. The fourth method for estimating cost is the trended historical cost method, and it obtains an estimate of reproduction cost by trending the historical cost with a factor from the cost index. Cost manuals organize cost factors in schedules or tables. Manuals can be developed locally or by third parties. A good cost manual is based on actual cost, and it is easy to use and update. Structure classifications should match the structure types found in the jurisdiction. Cost trend factors are necessary to adjust costs in manuals for time and location. A cost trend factor is derived from a cost index. A factor for time would divide the index for the current date by the index for the base date. Trending can work well for only a few years. Periodically, costs must be updated item by item if they are to remain accurate. End section. You may turn the page.